September 15, 1916, 5:50 a.m., Delville Wood, Somme. The German machine gunner stopped firing mid-burst, his hands frozen on the Maxim's grips as he stared at the shape emerging from the morning mist. It looked like a house had grown legs and learned to crawl. Steel plates bolted at harsh angles, tracks grinding earth and wire alike, moving at a walking pace toward his position. He grabbed the field telephone with hands that suddenly wouldn't stop shaking. "Panzerwagen," he shouted into the receiver, inventing a word because German military vocabulary contained no term for what he was witnessing. "A moving fortress! Bullets do nothing!" The officer on the other end of the line assumed panic or shell shock. Within minutes, that officer would be retreating from a weapon that military experts on both sides had declared impossible, a machine built not by generals or engineers with military credentials, but by a 50-year-old factory mechanic named William Tritton, who had spent his life building agricultural equipment and had never designed anything for war until someone asked him to solve the unsolvable problem of crossing barbed wire while surviving machine gun fire. What German commanders couldn't know, what would take them 2 years of catastrophic losses to fully understand, was that the crude mechanical monster grinding toward their trenches wasn't an aberration or a desperate experiment. It was the prototype for a weapon category that would dominate land warfare for the next century. The Mark I tank, 28 tons of riveted boilerplate wrapped around a Daimler engine and Holt tractor tracks, was simultaneously the worst tank ever deployed and the most revolutionary weapon system since gunpowder. It broke down constantly, poisoned its own crews with carbon monoxide, and moved slower than a running man. Yet it would break the stalemate that had killed a generation, render obsolete the defensive systems that dominated the Western Front, and fundamentally change how wars would be fought forever. This is the story of William Tritton, the forgotten mechanic who built the tank that saved Britain. Not through military genius or strategic vision, but through agricultural problem-solving applied with desperate urgency to the greatest military crisis of the era. The Western Front in 1915 was a killing ground without precedent. Machine guns firing 600 rounds per minute made infantry advances suicidal. Artillery turned battlefields into moonscapes of shell craters and mud. Barbed wire entanglements, sometimes 30 yards deep, channeled attackers into machine gun kill zones. The mathematics of assault were simple and fatal. Attacking forces suffered 10-to-1 casualty ratios against entrenched defenders. The first day of the Somme offensive, July 1, 1916, demonstrated the impossibility. 19,240 British soldiers killed in a single day, most in the first hour, for gains measured in hundreds of yards. British military leadership understood that continuing these tactics meant bleeding the army to death for no strategic gain, but alternatives didn't exist. Artillery bombardments that lasted days couldn't destroy well-constructed German positions. Infantry couldn't cross no man's land fast enough to reach trenches before machine guns cut them down. Cavalry was helpless against wire and bullets. Every conventional approach had been tried and failed. The war had become a mathematical problem without a military solution. Then, in January 1915, Lieutenant Colonel Ernest Swinton of the Royal Engineers wrote a memorandum proposing an unconventional approach: armored vehicles on caterpillar tracks that could cross trenches, crush wire, and survive rifle and machine gun fire. The idea wasn't entirely new. Armored cars had been tried and failed in mud. But Swinton had observed American Holt agricultural tractors used by British artillery units and recognized that tracked vehicles could traverse terrain where wheels couldn't. What if someone built an armored fighting vehicle using tractor technology? The War Office rejected the proposal. Senior officers argued that tracked vehicles would be too slow, too vulnerable to artillery, too unreliable for military use. The Admiralty, under Winston Churchill, showed more interest. Churchill, always fascinated by technological solutions, formed the Land Ships Committee in February 1915 to investigate whether armored tractors could work. The name land ships reflected naval thinking. The Admiralty imagined armored vehicles as ships that operated on land rather than sea. The committee needed someone who understood tracked vehicle construction. They approached William Foster and Company of Lincoln, an agricultural machinery manufacturer that had been building steam tractors and threshing equipment since 1856. The company's managing director was William Tritton, a 50-year-old mechanical engineer who had never designed military equipment but understood everything about building heavy machinery that could operate in harsh conditions. Tritton was an unlikely candidate for revolutionizing warfare. Born in 1865 in Horncastle, Lincolnshire, he had apprenticed as an engineer, worked for various agricultural machinery firms, and joined Foster and Company in 1905. His expertise was steam engines, tractor mechanics, and industrial machinery, practical engineering far removed from military technology. When the Land Ships Committee approached him in July 1915 with specifications for an armored fighting vehicle, Tritton's response was characteristically blunt. The specifications were impossible. The committee wanted a vehicle that could cross 8-foot trenches, climb 4-foot walls, survive machine gun fire, carry crew and weapons, and maintain reliability in combat conditions. No existing technology could meet all these requirements simultaneously. But Tritton agreed to try, not because he believed success was likely, but because the alternative, millions more deaths in static trench warfare, was unacceptable. The committee assigned Lieutenant Walter Gordon Wilson, a Royal Naval officer and automotive engineer, to work with Tritton. Wilson brought theoretical knowledge and naval engineering perspective. Tritton brought practical machinery construction experience. Together, they began solving an impossible problem using agricultural engineering principles.
The first challenge was mobility. Wheels couldn't cross trenches or navigate shell-cratered terrain. Tracks could, but existing track systems weren't designed for combat loads. Tritton studied Holt tractor tracks, which distributed weight across large surface area, providing flotation over soft ground. But Holt tracks were designed for agricultural speeds of 2 to 3 miles per hour, not military maneuvering. They needed to be stronger, wider, and equipped with cleats that could grip mud, climb obstacles, and maintain traction while crossing trenches. The second challenge was armor. The vehicle needed protection against rifle and machine gun fire without becoming so heavy it couldn't move. Tritton chose boilerplate, steel sheets 8 to 10 millimeters thick used in steam engine construction. Boilerplate could stop rifle bullets and many machine gun rounds while being available from industrial suppliers familiar with working it. The armor would be riveted rather than welded, using techniques Foster and Company already employed in steam tractor construction. The third challenge was trench crossing. An 8-foot trench couldn't be crossed by a vehicle that was only 15 feet long. Physics required the vehicle to be longer than the obstacle. But longer vehicles were harder to steer and more likely to become stuck. Tritton's solution was radical. Extend the tracks around the entire vehicle in a rhomboid shape, placing the track's highest point at the front top and lowest point at the rear bottom. This configuration meant the tracks were always in contact with both sides of a trench, allowing the vehicle to bridge the gap and climb out using its own weight and traction. The first prototype, built in August-September 1915, failed completely. Nicknamed Lincoln Machine No. 1, or Little Willie, it was a box-shaped armored vehicle on short tracks that could barely move under its own 14-ton weight and couldn't cross trenches wider than 4.5 feet. Everything about it was wrong. Too heavy, too short, insufficiently powerful. But it proved the concept might work if everything was redesigned from scratch. Tritton and Wilson started over. The second prototype incorporated lessons from the first failure. The hull was lengthened to 32 feet. The tracks were extended around the entire vehicle in the rhomboid configuration. Armament sponsons, armored projections mounted on the sides, would carry naval 6-pounder guns or machine guns. The engine, a Daimler sleeve valve petrol engine producing 105 horsepower, was mounted internally. The crew would consist of 8 men, commander, driver, 2 gearsmen, and 4 gunners. This second prototype was completed in January 1916. It was nicknamed Mother. The name reflected both its size and its role as the progenitor of future tanks. On January 16, 1916, Mother first ran under its own power. Triton watched from the factory yard as the 28-ton vehicle lurched forward, tracks grinding, engine roaring, moving at about 3 miles per hour. It looked absurd, a massive steel rhomboid that seemed to violate every principle of mobile warfare, but it moved. The demonstration for military officials occurred on February 2, 1916 at Hatfield Park. Winston Churchill attended, along with War Office representatives and Lord Kitchener, the Secretary of State for War. Mother crossed trenches, crushed barbed wire, climbed steep slopes, and survived rifle fire. The vehicle was loud, slow, and clearly difficult to control, but it worked in ways that nothing else had. It solved problems that military experts had declared unsolvable. Kitchener remained skeptical. He reportedly dismissed the vehicle as a pretty mechanical toy that would be destroyed by artillery and serve no military purpose. But others saw potential. The order was placed: 100 vehicles, designated Mark I, to be produced as quickly as possible for use in the next major offensive. William Foster & Company had less than 6 months to transform a hand-built prototype into a production vehicle. The production challenge was immense. Foster & Company had never built anything like a tank. Neither had anyone. No production templates existed, no supply chains were established for the specialized components. Triton had to source armor plate, design track links that could be manufactured in quantity, develop assembly procedures, and train workers who had only ever built agricultural machinery. The company's workforce, primarily skilled in steam engine construction, had to learn an entirely new type of manufacturing. The secrecy requirements complicated everything. The vehicles were officially described as water carriers or tanks for Mesopotamia, disguising their actual purpose as weapons. Workers were told they were building mobile water storage units. Only senior staff knew the truth. This security-driven deception meant that normal industrial consultation couldn't happen. Triton couldn't ask other manufacturers for advice or share specifications because doing so would reveal the project. The first production Mark I tanks were completed in June 1916. They incorporated improvements over Mother based on testing, but they retained fundamental limitations. The rhomboid hull made them difficult to steer. Turning required 3 crew members coordinating. The driver controlled the throttle and primary direction, while 2 gearsmen operated independent gearboxes for each track. Communication between these crew members was nearly impossible due to the engine noise and the lack of any internal communication system. Steering the Mark I was described by crews as like trying to sail a ship in a storm while blind and deaf. The internal environment was hellish. The engine, mounted inside the crew compartment, generated temperatures exceeding 100 degrees Fahrenheit. Exhaust fumes, containing carbon monoxide, accumulated inside the poorly ventilated hull. Crews could only operate for 35 to 45 minutes before becoming incapacitated by heat and poisoning. The armor, while effective against bullets, caused splash, molten lead fragments that sprayed inside the vehicle when bullets struck outside. Crews wore chainmail face masks to protect against splash, a medieval solution to a modern problem. Despite these limitations, 49 Mark I tanks were shipped to France in August 1916 for use in the Somme offensive. The crews, drawn from the motor machine gun service and hastily retrained as the heavy section machine gun corps, received minimal preparation. Many saw the inside of a tank for the first time days before combat. Mechanical training was abbreviated. The vehicles were too new and too scarce for extensive practice. Tactical doctrine didn't exist because nobody had ever used tanks in combat before. September 15, 1916. The Battle of Flers-Courcelette. Of the 49 tanks allocated to the attack, only 32 reached the starting positions. The others broke down during the approach march, demonstrating the mechanical unreliability that would plague early tanks. At 5:15 a.m., the 32 serviceable Mark I tanks advanced towards German positions near Flers, Delville Wood, and Ginchy.
The German reaction was immediate and panicked. Soldiers in the forward trenches had been trained to defeat infantry attacks with concentrated machine gun fire and artillery. The tanks absorbed machine gun bullets without apparent effect and kept advancing. Trenches that had been impassable obstacles for infantry were crossed by the tanks in seconds. Barbed wire that had funneled every British attack into kill zones was crushed flat under 28-ton steel treads. Unteroffizier Friedrich Steiner, manning a machine gun nest near Delville Wood, later described watching a Mark I approach. "We opened fire at 300 meters. The bullets did nothing. They sparked against the armor like striking flint. The machine crossed our trench, stopped, turned, and fired directly into our position. My entire section was destroyed. I ran. So did everyone else. The machine pursued us at walking pace, destroying everything in its path. We had no defense against it." The September 15th attack captured more ground than the previous 2 months of fighting. Villages that had resisted dozens of infantry assaults fell to combined tank and infantry operations within hours. But the success was limited by mechanical failures and tactical inexperience. Of the 32 tanks that started the attack, only 9 reached their final objectives. The rest broke down, became ditched in shell craters, or were abandoned when crews succumbed to carbon monoxide poisoning. One tank, designated D1, made it to Flers village center and became legendary when aircraft observers reported a tank is walking up the high street. The psychological impact was immense, but the practical results were mixed. German intelligence reports from September 1916 struggled to describe what had happened. The term tank hadn't entered German military vocabulary yet. Reports referred to Panzerkraftwagen, armored motor vehicles, gepanzerte Raupenschlepper, armored caterpillar tractors, or simply mechanical monsters. German High Command initially dismissed tanks as British propaganda or experimental curiosities that posed no serious threat. But frontline reports told a different story, that defensive positions optimized to stop infantry were helpless against armored vehicles. British press coverage of the tank debut was enthusiastic but vague due to censorship. Newspapers reported a new secret weapon without providing details. The secrecy persisted until November 1916, when enough information had leaked that full censorship became pointless. By then, dozens of Mark I tanks had been captured or destroyed, allowing German engineers to study the design and understand exactly what they faced. William Triton received no public recognition. His name didn't appear in press coverage. The heavy section machine gun corps crews were the public heroes, men who operated the tanks under impossible conditions and suffered catastrophic casualties. But Triton continued refining the design. The Mark I's flaws were obvious. The steering system was unworkable, the ventilation was inadequate, the armor was too thin against armor-piercing ammunition. Work began immediately on Mark II, Mark III, and Mark IV variants, incorporating improvements. The Mark IV, introduced in June 1917, addressed many of the Mark I's worst problems. Armor thickness increased to 12 millimeters, stopping armor-piercing machine gun rounds. The sponsons were redesigned to be removable, allowing tanks to be transported by rail more easily. The fuel system was improved to reduce fire risk. but the fundamental design remained Tritton's rhomboid hull with tracks running the entire length. This configuration proved optimal for trench crossing and became standard for British tanks throughout the war. The Battle of Cambrai in November 1917 demonstrated what massed tank operations could achieve. 476 tanks attacked on a 6-mile front without preliminary artillery bombardment. The surprise was complete. German defenses collapsed. The tanks crossed the Hindenburg Line, Germany's most sophisticated defensive system, in hours. British forces advanced 4 miles in the first day, the deepest single-day advance since 1914. But exploitation failed due to the tank's mechanical limitations and the inability of infantry and cavalry to keep pace. The Germans counterattacked and recaptured most lost ground within 2 weeks. Cambrai proved that tanks could break static defenses, but revealed that the entire military system needed redesign to exploit armored breakthroughs. Infantry tactics, artillery coordination, logistics, communications, everything had to evolve to match the capabilities of the new weapon. This evolution would take decades, extending far beyond the First World War into mechanized warfare doctrines of the 1930s and 1940s. German response to tanks was confused and reactive. They developed armor-piercing ammunition and tactics for engaging tanks at close range with grenades and captured weapons. But they never matched Allied tank production. Germany produced only 20 A7V tanks, their indigenous design, during the entire war. Instead, they relied primarily on captured British tanks, eventually operating more British armor than they had of their own manufacture. This dependence on enemy equipment demonstrated how thoroughly Germany had been caught unprepared for armored warfare.
The first tank versus tank combat occurred on April 24, 1918 at Villers-Bretonneux. 3 British Mark IV tanks encountered 3 German A7Vs. The engagement lasted 7 minutes and ended inconclusively. 1 British tank was disabled. German tanks withdrew after return fire. Neither side achieved tactical victory, but the engagement established that future tank warfare would involve armored vehicles fighting each other, requiring new doctrines, new weapons, and new designs optimized for anti-tank combat. By the war's end in November 1918, Britain had produced 2,636 tanks of various marks. France had produced 3,900 Renault FT-17 light tanks, a design that influenced tank development more than the Mark I because it introduced the now standard configuration of turret-mounted gun and rear-mounted engine. The United States had planned massive tank production, but the war ended before American factories could deliver significant numbers. The tank had transformed from experimental curiosity to essential weapon system in less than 3 years. William Tritton received a knighthood in 1917 for his contributions to tank development. The honor was granted quietly. Full public recognition would have violated wartime security. After the war, Tritton returned to agricultural machinery manufacturing. Foster & Company continued building tractors and industrial equipment. The tank production facilities were dismantled. The company never built military vehicles again, though it had created the prototype for one of the most important weapons of the 20th century. Tritton rarely spoke publicly about his role in tank development. When interviewed in the 1920s, his comments were modest to the point of self-effacement. "We built what was needed using the materials and methods available to us. The credit belongs to the men who operated the vehicles under impossible conditions, not to those of us who built them in the relative safety of factories." This modesty obscures the revolutionary nature of Tritton's achievement. He didn't invent the concepts that went into the tank. Tracked vehicles, armor, and weapons all existed before 1915. His contribution was synthesis, combining existing technologies in a configuration that solved a problem military experts had declared unsolvable. The Mark I tank was primitive, unreliable, and barely adequate, but it was adequate. It worked well enough to break the stalemate, force evolution of tactics and doctrine, and create a new category of weapon that would dominate land warfare for a century. The human cost of pioneering tank warfare is often forgotten in discussions focused on technical achievement. Tank crew casualties in World War I exceeded 50% in some units, higher than infantry in the same battles. Crews died from carbon monoxide poisoning, heat exhaustion, burns from engine fires, bullet splash, and being trapped in overturned tanks that had no emergency exits. The Medal of Honor, Victoria Cross, and other highest military decorations were awarded to tank crews, but many recipients died in the actions that earned recognition. Captain Richard Wayne, commanding C Company of the Heavy Machine Gun Corps at Cambrai, wrote a letter home 3 days before being killed in action. "The tank is hell incarnate. The heat, the noise, the fumes, the impossibility of communication, the constant mechanical failures, yet we continue because infantry follows us across ground they couldn't take in a year. The machine is horrible, but it ends the slaughter. I would rather die in a tank knowing we're winning than die in a trench knowing we're losing." Post-war analysis of World War I tank operations reached contradictory conclusions. Conservative military theorists argued that tanks had been a temporary solution to trench warfare's unique conditions and would be obsolete in future conflicts. Progressive theorists, including British officers J.F.C. Fuller and Basil Liddell Hart, argued that tanks represented the future of warfare and should become the foundation of military doctrine. Interwar years saw these competing visions play out in divergent paths of tank development across different nations. Britain, despite having pioneered tank warfare, allowed its lead to erode through budget cuts and doctrinal confusion. By 1939, Britain's tank force was smaller and less capable than Germany's, despite British tanks often having superior armor and armament. The problem wasn't technology, it was doctrine. Britain had invented the tank, but never fully committed to mechanized warfare doctrine that would exploit its potential. Germany, forbidden by the Versailles Treaty from developing tanks, studied Allied tank warfare with the intensity of those who had been defeated by it. German officers, including Heinz Guderian, studied British and French tank operations and drew lessons that would become blitzkrieg doctrine. When Germany began rearming in the 1930s, their tank development focused on combined arms coordination, tanks working with motorized infantry, artillery, and air support. The irony was brutal. Germany perfected the operational concepts that British pioneers like Triton, Fuller, and Liddell Hart had advocated, which the British military had failed to implement. The Soviet Union pursued mass tank production and developed deep operation theory that anticipated modern armored warfare. By 1941, the Soviet Union had more tanks than all other nations combined, over 20,000 vehicles. Many were obsolete, but the quantity reflected a strategic commitment to mechanized warfare that other nations hadn't matched. When Germany invaded in June 1941, Soviet tank forces were destroyed through tactical incompetence and operational surprise, but Soviet industrial capacity allowed replacement and expansion that Germany couldn't counter. The technical lineage from Triton's Mark I to modern main battle tanks is direct and traceable. The rhomboidal hull proved unsuitable for anything except trench crossing and was abandoned by the 1920s. But the fundamental concept, tracked armored vehicle carrying weapons, remained unchanged. The Renault FT-17's rotating turret became standard. British experiments with suspension systems influenced Soviet T-34 development. American industrial production techniques enabled mass manufacture of 88,000 tanks during World War II. Every innovation in armored warfare traces ancestry to solutions first implemented in desperate attempts to make Triton's agricultural engineering work in combat. At the Tank Museum in Bovington, England, sits one of the few surviving Mark I tanks. Visitors examine it with confusion. The design seems bizarre, almost comical. The rhomboidal hull appears ungainly. The side-mounted sponsons look vulnerable. The entire concept seems obsolete. Museum guides explain that this primitive vehicle revolutionized warfare. Most visitors struggle to connect the crude machine before them with the sophisticated armor forces of today. The disconnect highlights how revolutionary technology often emerges from unexpected sources and appears primitive compared to its refined descendants.
Modern main battle tanks weigh 60 to 70 tons, travel at 40+ miles per hour, carry sophisticated electronics and composite armor, and cost millions each. The Mark I weighed 28 tons, traveled at 3.7 miles per hour, had no electronics, and cost approximately 5,000 pounds. The technical evolution is enormous, but the fundamental mission, crossing hostile terrain while surviving enemy fire and delivering firepower, remains identical to what Triton designed in 1915-1916. The Mark I was the answer to an impossible question. Every tank since has been a refinement of that answer. William Triton died in 1946, age 81, having lived to see tank warfare reach maturity in World War II. His obituaries focused on his engineering career and business achievements. His role in creating the tank received brief mention. The full story of how a mechanic with no military background had designed the weapon that broke the Western Front remained largely unknown. Triton himself never claimed more credit than he believed appropriate. He consistently described his work as applied engineering, nothing more. But that applied engineering changed history. The Mark I tank was crude, unreliable, dangerous to operate, and barely adequate for its intended purpose. It was also the weapon that ended static trench warfare, forced evolution of mobile combined arms tactics, and created a new category of warfare that would dominate the 20th century. Triton built it because he was asked to solve a problem and applied agricultural machinery principles to military requirements. The fact that his solution revolutionized warfare was almost incidental. He was just trying to build something that worked well enough. The Germans who faced tanks at Flers Courcelette in September 1916 were confronted with a weapon that violated their understanding of warfare. Their defensive doctrine, perfected over 2 years, suddenly became obsolete. Machine guns that had stopped dozens of infantry attacks couldn't stop armored vehicles. Trenches that had been impassable became minor obstacles. The entire system of static warfare collapsed when confronted with a solution to the mobility problem. That solution came not from military innovation, but from agricultural engineering. Triton built tractors. When asked to build something that could cross trenches and survive bullets, he built an armored tractor. The fact that this solved the greatest military crisis of the era wasn't military genius, it was practical problem-solving applied with desperate urgency to an impossible challenge. September 15, 1916, 32 Mark I tanks cross no man's land. By November 1918, over 2,600 British tanks have been produced. By September 1939, every major military power has armored forces. By 1945, tank warfare has become the dominant form of land combat. By 2025, main battle tanks remain central to military planning. The straight line connecting all these developments traces back to William Triton's workshop in Lincoln, where a mechanic who had never designed military equipment solved the problem that military experts couldn't solve. The death ray that Tesla promised never materialized. The exotic weapons that seemed revolutionary proved impractical. But the tractor wrapped in boilerplate, built by an agricultural machinery company, changed warfare permanently, not through sophisticated technology, but through practical engineering applied to an urgent military need. The revolution wasn't in the innovation, the components all existed. The revolution was in the synthesis. in recognizing that agricultural machinery principles could solve military problems that military thinking couldn't address. The thunder of tanks crossing the Somme in September 1916 wasn't just mechanical noise, it was the sound of warfare transforming, of static defense breaking, of military certainty collapsing. The Germans heard it and knew their advantage had ended. The British heard it and knew their sacrificial infantry attacks could be replaced. The world heard it and recognized that future wars would be mechanized, all because one forgotten mechanic built a machine that worked well enough to matter. William Triton built the tank that saved Britain, not through military genius or strategic vision, not through sophisticated science or revolutionary technology, but through agricultural engineering applied with desperate pragmatism to the greatest crisis of the era. The Mark I was crude, inadequate, barely functional. It was also exactly what the situation required, and because it was exactly enough, warfare changed forever. The farmers turned tractors into weapons. The mechanic built the machine. The Germans stopped laughing, and the war that seemed unwinnable became winnable because someone asked a tractor engineer to solve a problem, and he did.